Welcome to general solutions to homogeneous constant coefficients ODEs. So recall we have seen if the characteristic polynomial of a constant coefficient homogeneous linear nth order ODE has n distinct real roots R1 through Rn, then y1 equals e to the R1x through yn equals e to the Rnx, form a fundamental set of solutions. So the question becomes, what happens if the characteristic polynomial has repeated real roots? We know what happens in the second order case. Does the same thing apply for third order? So for example, let's find the general solution to the third derivative of y minus the second derivative minus the first derivative plus y equals 0. So this we can write with the derivative operator. So writing with the derivative operator, we have d cubed minus d squared minus d plus 1, all applied to y is equal to 0. D cubed minus d squared minus d plus 1 actually factors as d minus 1 squared times d plus 1. So we have d minus 1 squared applied to d plus 1 applied to y is equal to 0. So we can reduce our problem. So we can reduce the problem to d minus 1 squared applied to y equals 0 and d plus 1 applied to y is equal to 0. So this first equation, d minus 1 squared applied to y equals 0, corresponds to the characteristic equation, r minus 1 squared equals 0. And so we would have y1 is e to the x, and y2 is x e to the x, which is what we learned for second order equations. The second one, essentially we have, we could view it as characteristic equation, r plus 1 equals 0. And we get y3 is therefore e to the negative x. And so we have general solution y equals c1 e to the x plus c2 x e to the x plus c3 e to the negative x. Now this took care of the case where we have a real root repeated twice, but what happens if it appears more than twice? Again, now that we're beyond second order, we could certainly have a real root appear n times if we wished. So we get a theorem for this, which is that the equation given by d minus a to the k applied to y equals 0. This equation has fundamental set of solutions y1 is equal to e to the ax, y2 equal to x e to the ax. And then from here on, we're just going to keep on adding factors of x until we hit our nth solution. So we will have yn is equal to x to the n minus 1 times e to the ax. So for example, if we have d minus 3 to the 7th power applied to y is equal to 0, then we would have general solution y is equal to, I'm going to pull out the e to the 3x, and we would have c1 plus c2x plus c3x squared plus all the way through c7x to the 6th. So if we have a equation whose characteristic polynomial has a nth or a kth repeated root, we can break it down, boil it down to that reduced k power or kth order equation and use this theorem to solve for solutions for that component. Similarly, what if a characteristic polynomial has complex roots? So we already saw an example of this in the previous video, but let's go ahead and do one more. So let's find the general solution to the third derivative of y plus the second derivative plus 3 times the first derivative minus 5y is equal to 0. So if I remember correctly, first apply the derivative operator. This is d cubed plus d squared plus 3d minus 5, all applied to y is equal to 0. And if we factor this polynomial operator, if I remember correctly, this is d plus 1 times, actually I believe it's d minus 1, sorry, d minus 1 times, we would need d squared to get to d cubed, then that would be a minus 1d squared, so we need plus 2d squared. We would get that by plus 2d times our d. Now we have a minus 2d, so we need a plus 5, and that does indeed give us our minus 5 in the end. This all applied to y is equal to 0. And so we get our two reduced equations. We will be looking at d minus 1 applied to y is equal to 0. And we will be looking at d squared plus 2d plus 5 applied to y is equal to 0. This first one, we have characteristic polynomial, r minus 1 is equal to 0. And so we get that our y1 is just e to the x. The second one would have characteristic polynomial r squared plus 2r plus 5, or r plus 1 squared plus 2 squared, and then this is equal to 0. This would give us complex roots. Y1 is equal to e to the negative x cosine of 2x. Sorry, y2 is equal to e to the negative x cosine of 2x. And y3 is equal to e to the negative x sine of 2x. And so in this case, we would get general solution of y is equal to c1 e to the x plus C2e to the negative x cosine of 2x plus C3e to the negative x sine of 2x. Once again, we were able to boil this down to a second order equation. We know how to solve those second order equations where we have the complex roots of our characteristic polynomial. And so we could solve directly from there. Now we're going to run into a complication we have not seen before, which is what if the characteristic polynomial has repeated complex root? So this can happen as long as we have a fourth order polynomial or higher. So let's go ahead and take a look at the equation, just the general equation with repeated complex root, which we will write as d minus lambda squared plus omega squared, all applied to y equals 0. So again, oh, sorry, I missed so we'll have d minus lambda squared plus omega squared, all raised to the kth power, and then applied to y equals 0. So this will have complex root lambda plus or minus omega I repeated k times. This has fundamental set of solutions. Y1 is e to the lambda x cosine of x, sorry, cosine of omega x. Y2 will be x e to the lambda x cosine of omega x. And we will go all the way up through yk is x to the k minus 1 e to the lambda x cosine of omega x. In addition, we will have the same thing for sine. So we will have yk plus 1 is e to the lambda x sine of omega x. And then we will go up through y sub 2k, which will be x to the k minus 1 e to the lambda x sine of omega x. So essentially, just like we had for repeated real root, for every additional repetition of our root, you just add in more solutions with another factor of x. So for example, let's find the general solution to the fourth derivative of y plus 18 times the second derivative plus 81 times y equals 0. So this becomes d to the fourth plus 18d squared plus 81 all applied to y is equal to 0. This factors as d squared plus 9, the whole thing squared, applied to y is equal to 0. So in this case, our lambda is just 0. Our omega will be 3, since 9 is 3 squared. And our k is 2. And so we get our y1 is just cosine of 3x. Y2 will be x cosine of 3x. Y3 will be sine of 3x. And y4 will just be x sine of 3x. Putting this all together, we get general solution. We will have y is equal to c1 plus c2 x, c1 plus c2x times cosine of 3x plus c3 plus c4x times sine of 3x. So this is how we can go about solving our ODEs when we have whatever roots we have, however many repetitions of complex roots, however many repetitions of real roots, this should satisfy any characteristic polynomial if we can find those roots.